So the last topic we're going to have is we're going to see how the frequency that we hear of sound is going to change depending on motion. We've all experienced this in everyday life. For example, if you're standing on the side of the road and an ambulance passes, you notice that as it approaches you, you hear a higher pitch in the siren than you do when it's moving away. And the reason for this is something called the Doppler Effect. So to see how it works, let's say we're driving in a car, and we're driving toward a stereo that's emitting sound at a single frequency. Okay, so these sound waves are moving towards us at a speed that we'll call the speed of sound, c sub s, and we're moving toward those at a speed v. So as we're approaching, recall from our unit on circular motion and reference frames that we said that the speed of sound that we hear is going to be equal to the speed of sound in the non-moving frame plus our velocity. So it's going to seem to be moving faster. Of course, later, when we're moving away with the speed v, now the speed of sound is going to be coming up from behind us. So as we're retreating, we see that the speed of sound is going to be the speed of sound minus our velocity. We're going in the opposite direction. So it takes a little while to prove, and I'm not going to bother doing it, for these lectures. But what you'll see is if the frequency f0 is the frequency that was being emitted by the stereo, then for the approaching sound waves, the frequency we hear would be f0 times the speed of sound plus v over the speed of sound. The frequency we hear when we're moving away would be the speed of sound minus our speed over the speed of sound. So we see that as we're approaching, we would get a higher frequency. As we're retreating, we would get a lower frequency. And we can understand why. It has to do with how fast the sound is moving towards us. Okay? The second example is, now what if we have a moving source? So now let's say that we're stationary and we're just standing here, but now we have our stereo is on like a skateboard or a car or something like that, so it's moving towards us. Okay, so at the closest time to us, those would be the waves that are the furthest away. But before that, when it was a little bit further away, it would have at an earlier time, it would have let out a different sound. It would have let out sound from a different point. If we move a little further back in time, again, it would have let off, sound from a different point. And the sound, of course, the circular wave is going to be centered on where he emitted it from. So this yellow dot is where he emitted it, the wave that's closest to us. He's moving towards us. So, the next instant he emits another wave, but it hasn't had as much time to propagate as the yellow one. A little later, he's at the blue spot, he emits that wave. And so we see that on the end closest to us, that these waves are kind of bunched up together. Whereas the ones that are further away, on the back end are getting further and further apart. And so, as you can imagine, that's this is really where the shift in frequencies comes from. Okay, so again, so if he's approaching us, then the speed of sound that we hear is going to be the speed of sound the speed of sound plus the velocity v that it's moving towards us. The frequency that we hear is going to be the frequency that it's emitting at in its frame times the speed of sound divided by the speed of sound minus its velocity. And if it was moving away, so if it was going in the opposite direction, the speed of sound would be that we hear would be the speed of sound minus the velocity of that the stereo is moving. So the frequency we hear would be the frequency that it's emitting times the speed of sound over the speed of sound plus its velocity. So again, when it's approaching us, we hear a higher frequency. When it's heading away from us, we hear a lower frequency. And so it's the same effect that describes both situations. Okay? So in general, now, so let's look at the general case now, because this only had, in one case, we were moving, so we usually call that the detector. So we had, V detector, we're moving. In the second case, we had the source moving, but of course, in general, we can both be moving. So for example, let's say the source is moving to the right, the detector is moving to the left, so they're both moving towards each other. Okay? In this case, the frequency that we hear, that the detector hears, is the frequency emitted times the speed of sound plus the velocity of the detector divided by the speed of sound minus the velocity, the speed of the source. If the source is moving toward the detector and the detector is moving away, then the frequency that the detector would hear is the emitted frequency times the speed of sound. Now it's going to be minus the speed of the detector because it's moving away, so it should get smaller. But it's still the speed of sound minus the velocity of the source because the source is moving toward the detector. So we see that if those two velocities are the same, then the detector would hear the exact same frequency that was emitted. Of course, we could have the source moving away from the detector and the detector moving toward the source. In this case, the frequency is the frequency emitted times the speed of sound plus the speed of the detector divided by the speed of sound plus the speed of the source. So again, if they're both moving at the same speed, then we would just hear the same frequency, as if neither of them was moving. Of course, the last case, we can have the source moving away and the detector moving away. So in this case, the frequency is the frequency that we hear times the speed of sound minus the velocity of the detector divided by the speed of sound plus the velocity of the source. And so these are the four different situations that we can have. And this is basically how our radar detector works. So a police officer would stand over here with a radar detector, and it would send a bunch of sound waves to bounce off of a source. They'll come back shifted because the source has moved away, and then this detects that shift and it converts that into a velocity. Because as you see here, if we look back at our equation where we had just the source moving, we see that we could solve this equation for velocity, and so we can find out what the velocity is as long as we can detect the change in frequencies. This is also actually a technique that astronomers use, and this is one of the ways that we've found out that galaxies are moving away from us, because it turns out not only is the sound work like this, but light is another type of wave. And so we can look at light waves, and light waves are actually have their frequency shifted, which means their color is shifted. So things that are moving away from us appear more red than they actually are, and things moving towards us are more blue. And as to why that is, that's kind of a deeper subject for another day. But now as the course is kind of coming to a close, you see that you really have a lot of tools to start talking about and describing a lot of different phenomena. In the next semester, you're going to be, kind of picking up here. You're going to start talking about electricity and magnetism, and the course from as far as I understand is going to be the exact same format. You're going to be taking unit exams, and you'll take them when you're ready, and you'll progress through. You're going to have videos online and everything, just like for this semester. So thank you all very much. It was a pleasure having you in class this semester and interacting with y'all and seeing everybody learn. And hopefully you enjoy the semester as much as non-physics majors can enjoy physics. And I hope you have a good rest of your summer.